So let's say that this graph models the position of your car at any point during your trip. Now, if we wanted to know this number, all we would do is we would take, let's say this is our point A, and this is our point B. If we wanted to know the average velocity, we would take, this is our function f of x, we would take f of b minus f of a over b minus a. Because that's just like our change in position over our change in how long it took us to get there. That's our total distance divided by our total time. And what is this, though? What is this object? This is a slope. But what is it the slope of? It's the slope of the line connecting those 2 points. And we call that line the secant line. And it's just a line that connects 2 points by a straight line. So here's the problem. This gives you the average velocity for your trip, but what if you wanted to know the velocity at a specific time? Let's say you wanted to know your velocity there, or at A. How would you do it? Well, you could get a better approximation by taking the same graph but instead of taking a large interval, take a really small interval, because that'll give you the average time, the average velocity over a small time. That gets you really close to the velocity right there. But we can do better than this. We can say, well, what if the distance between these 2 points, we'll call this distance h. What if we let that distance go to 0? Then we'll get the slope of a line just at the single point. That'll give us the velocity at that exact point, because that's the average velocity where you are. So that's your instantaneous velocity. So what we do is we rewrite this formula, but now we're going to take a limit as the points approach each other. So we're going to say that we want to find the instantaneous rate of change, the instantaneous velocity of this point x. So what we do is we take some test point over here, some distance h away, and we write the slope of the line between them. So we say that slope is equal to the change in your f of x values. So we have our first point, which is f of x plus h, because it's f at x plus h, minus f of x divided by the change in x, which is h. So if we want the slope of this line here, all we have to do is let h go to 0. Since you're good students of calculus, you now know how to use limits. So we're going to take a limit. So we're going to say the slope of the line tangent to the curve, the tangent line, is equal to the limit as h goes to 0 of this. This is the instantaneous rate of change. This was the start of calculus. This is what Newton came up with to figure out, how do I know what is the instant velocity at some point? What is the velocity at some point in time that I can calculate? So this, you already have experience calculating. Let's see if we can figure out how to calculate slopes at some point using this. But before we move on, let's talk about a little notation. So it would be really annoying to have to write slope sub t every single time we wanted this. Well, if you notice, this is a function of x that's derived from the function you're looking at. So what we do is we call this the derivative of f. This is the derivative of f of x. And we denote that f prime of x. Okay? Another way we can write this is to say, well, if we look at this, we can write this as our change in f over change in x, just like you probably saw in high school. So you're changing y over change in x. We use delta to denote change in. When we take these very, very small change in, the change in x going to 0, we replace the deltas with d's. So we can write the derivative of f just like that. Okay? When we want to say find the derivative of f of x, we'll say this object means take the derivative of whatever's here. So let's do an example of this to see what this means. Okay, so I want to know what is the derivative of x. So what am I asking here? I'm asking what is the slope of the tangent line at any given point x. Okay, so we have to take a limit. Limit, as h goes to 0, of f of x plus h, which in this case is just x plus h, minus f of x, which is x, divided by h. So, if you notice, the x's cancel, and we're left with the limit as h goes to 0 of h over h. But that's equal to 1, because this is just 1. So what does this mean? That means at any point on this graph, the tangent line has a slope of 1. Well, why should that be? Why should the velocity be the same everywhere? That's the graph of that function, right? This is y equals x. No matter what point you're at, the tangent line is always the same there. So it always has the slope of 1, because that's the slope of the line. So let's do a slightly more complicated one. Let's say we want to find the slope of the tangent line on this parabola, y or x squared, at the point x equals 2. So I want to know what's the slope of that line. Okay, so let's do that. So again, we're going to have to do this limit definition of a derivative and calculate what is the function that tells us the slope. So let's do it. Take the derivative of x squared. Okay, so we start with our limit. Now we have to do f of x plus h. So that's going to be x plus h, quantity squared, minus f of x, all divided by h. Okay, so we need to expand this binomial here so we can start canceling terms. So we get our limit. So this gives us x squared plus 2xh plus h squared minus x squared all over h. All right. Well, if you notice, that cancels with that. So we're left with limit as h goes to 0 of 2xh plus h squared over h. Okay, so since there's an h in both terms in the top and an h in the bottom, what we can do is we can cancel an h from each of those. So what we're left with is this limit of 2x plus h. Now remember back to your limit rules, when you have a limit of a sum, you can just apply the limit to both terms in the sum. So limit as h goes to 0 of 2x, well that doesn't change anything because it doesn't have any h dependence. And the limit as h goes to 0 of h is just 0. So we're left with the result that the derivative of x squared is equal to 2x. Now my question earlier was, what is the slope of the tangent line at x equals 2? Well, if we know our derivative as a function of x is 2x, we simply just plug in the value that we want. So the derivative at 2 is 2 times 2, so that's 4. So the slope of the line tangent to x squared at x equals 2 is 4. So now we've found, say you have a ball and you drop it, it would be modeled exactly like this. So if you wanted to find the velocity of the ball after 2 seconds, this is all you would do. You would take the derivative and plug in the point in time you're looking for. Okay? So polynomials aren't bad. As you notice, there's a pattern emerging here that everything without an h will end up canceling. That's what you want to look for, because if you get something without an h in the top not going away, then you can't cancel the h in the bottom when you're dividing by 0. That's a bad thing. So let's see where this might come up in another example. A little more complicated. So the example I want to do now is to take the derivative of the square root of x plus 2. Okay, so this one involves square root, so it's much more complicated than a polynomial. Well, let's go ahead and see if we can do it. So we start with our limit. All right, so we have f of x plus h, so that gives us x plus h plus 2 all under square root minus f of x, which is that. We divide by h. Okay, so here's the problem with this. As you can see from this, there's an h, but it's all tangled up in a square root function. There's no way to really cancel this h with that. There's no h here. There's no way to cancel these terms nicely. So what do we do? Well, if you remember back to your days to algebra, whenever you dealt with pesky square roots, one of the ways to solve this was to multiply by what's called the conjugate. So what we're going to do is we're going to try to get rid of square roots by multiplying by the conjugate, okay? And so we do that by multiplying by basically this, but with a plus sign instead. So we multiply by x plus h plus 2 plus the square root of x plus 2. Now we can only do this if we multiply the bottom by the same thing, because this essentially is multiplying by 1, which is totally allowed. Okay, so what does that give us? So, still have our limit. All right, the numerator, if you remember your laws of FOILing, if you have the same thing, but the negative and one is negative and one is positive, the middle terms are going to cancel because you're going to get this times this minus this times this, but those are the same thing. So all we have are this term and that term. So we're left with x plus h plus 2 minus x plus 2 in the top. In the bottom, we're left with h times x plus h plus 2 plus x plus 2. All right, so if we look at this, we have an x plus 2 and then a minus x plus 2. So the x's and the 2's all cancel each other out. So what we're left with is our limit, h in the top, h in the bottom, okay, so we can cancel these h's out. So now all we have to do is apply this limit to the h's. And there's only one h, so we can just plug in 0 for that h. So we're left with 1 over square root x plus 0 plus 2 plus square root of x plus 2. So when that goes away, we're just left with 1 over square root of x plus 2 plus square root of x plus 2. So that's simply 1 over 2 square root of x plus 2. And that is, in fact, the derivative of the square root of x plus 2. So when you're tackling these limit definition of a derivative, you always want to try to find a way to get your h's to cancel, because if not, bad things are going to happen. You probably won't be able to solve the problem. But in general, for polynomials, they'll always work out very nicely. They might be kind of long, but you can always do it. For square roots, if you're still using limit definition, Multiplying that by the conjugate is not a bad way to start. It's really hard to do a lot of these using the limit definition. So the next video is going to focus on trying to figure out how can we take derivatives without having to take these limits every time. Can we notice patterns so that we don't have to do all these limits? Okay, so that's next time. But this limit definition of a derivative usually gets put to the side and people forget about it. Don't do that. The limit definition really captures what a derivative is. It's the slope of a tangent line. And you can't forget that because that is the crucial part of derivatives. Derivatives is half of calculus. And if you forget that it's the slope of the tangent line, all your classes are all for naught. So try to remember that. Don't throw away the limit definition. And good luck.